Hello, can you guys hear me? Okay. Uh, so, welcome to the last class of the course. So, today we'll be doing a quick review of course material, basically, the things that you should focus on for your finals. Okay. So, just a reminder, final exam will be on May 3rd. So, similar to midterm, this will also be available for 24 hours. And you can choose any 90 minutes to attempt this exam. And another announcement, like course evaluations, please fill out the course evaluations. It provides me an opportunity to see what things we can improve about the course. And also I just want to understand like how like what are the problems you are facing, especially when the course when the course is remote, right? So this is the first time the course is offered in like rather hybrid or even remote fashion. So course evaluations will really help in understanding like the things that we need to keep in keep in the mind. And given that we will be redesigning the course for the next spring, the evaluations will really help me in making the course like in assuming that next quarter also it will be uh, like next spring, assuming that it would be online. So I really want to make sure that the course will be conducive for learning, so that all the small hiccups or whatever problems you're facing, especially during labs or during understanding materials or anything, we can fix them. Okay. So yeah, we'll be reviewing the second half of the semester, basically the things starting from dynamic memory to file systems. So we'll be doing a very quick review. We'll not be going into the details, but I'll be touching the high level concepts, or rather the topic headings, which you should study, or like which we should refresh your knowledge for finals. So yeah, page replacement policies. So this is for managing physical pages. So we have seen optimal, random. So random, we may not have seen it in like on slides, but you can imagine random as just a strategy where you randomly pick some page to be replaced. Okay. And we have seen FIFO, and we have seen the problems with FIFO, like Belladay's anomaly, where the number of page faults actually increases when you increase the physical frames, which is kind of counterintuitive, right? And we also saw LRU, and we saw how we can use counters to have an approximation of LRU by doing the left shift and using the reference bit from the page table entries. Okay. And we also saw FIFO with second chance, and we saw how we can use clock method to simplify the implementation of FIFO. We also saw how we can use dirty bit to make effective page replacement policy decisions, like basically give a lower preference to pages that are dirty, because that requires us to uh, write back the pages to the disk, right? So that's the page replacement policies. And then we also looked into thrashing and when thrashing happens. And a way to avoid thrashing is to maintain working set of each process and making sure that we don't do page replacements within the working set. And the size of working set also plays a major role uh, in efficiency and like effective use of the physical memory. And we also saw how processes can use shared memory, especially when process forks, how the memory is shared between multiple processes, where the page table entries are set read only, and how we can use copy on write mechanism to effectively share pages between parent and child. So this you have implemented this in lab 4, where you have actually done copy on write implementation. So that should give you some ideas of how copy on write will be implemented, and how, like in reality, how copy on write is implemented, right? So you maintain a counter for each physical frame. That's one way to do it, and you can think of different ways in which copy on write can be implemented. So the questions to think about when it comes to virtual memory is like the common questions, right? What is the uh, what is the advantage? What are the advantages of optimal algorithm? We know that it provides the best case performance, but it cannot be implemented in practice because it requires perfect knowledge for the future, which is not possible in reality. Okay, so we also know, like, okay, since future is unknown, what is the point of having a good page replacement policy, right? So this is because of locality. We know that processes have locality, so we exploit that, and using locality, you exploiting locality, we design different page replacement algorithms to make efficient use of the physical pages that we have. Okay, and there are different algorithms. Different page replacement policies have different requirements, but some page replacement policies can be implemented without hardware support. Some needs hardware support, and also a few page replacement algorithm, basically FIFO, like more page frames doesn't always imply less page faults because of FIFO, where we have Belady's anomaly. And then we also uh, saw how we can move page out of the critical path, basically maintain a set of free pages. That way, even when a process needs a page, we don't always have to page out, right? We can like other way that we can avoid paging out is to maintain the dirty bit. Dirty bit just allows us to replace a page without actually uh, saving the page, or like rather swapping out the page to the disk. And yeah, other virtual memory questions, like what are the advantages of per process versus global page replacement policies? Trashing, what causes trashing? What to do about trashing? What can we do? What is a working set, and benefits of copy on write? And can we avoid copy on write? And when exactly copy on write happens? So on and so forth. Okay. So, okay, yeah. Any questions on virtual memory, or like any doubts regarding the questions that would come in finals? Okay. Next, storage and file systems. So yeah, storage devices we mainly looked at magnetic disk and SSDs. We saw what are the components that contribute to the delay in magnetic disk, basically the seek and rotation delay. And we also saw a few very brief overview of SSDs and how uh, the writes are very inefficient because we need to do a block write for every write, right? So in order to make it more efficient, SSDs use FTLs. Does anybody know what FTL mean? So anybody, what does FTL mean? So TL stands for translation layer. Okay, that's the hint. What does F stands for? Perfect. Yes. Uh, yeah, flash translation layer. That's right. So it's similar to page tables. Flash translation layer is just a translation layer that converts from logical blocks that are exposed to the operating system to the actual physical blocks that are maintained within the SSD. Okay. And both disks and SSDs can fail. So in order to avoid that, we looked at RAID. RAID can be used for either performance or reliability, or in few cases, both performance and reliability. Right? Two main ideas in RAID are striping and mirroring. And the mirroring, we avoid, we also can do smart mirroring by using parity, where we can still recover from error without actually doing a complete mirroring of all the disks. We looked at RAID levels 1 to 6. And yeah, before RAID, actually, we looked into file system overview, like the basic file system abstraction provided by the operating system. What is file, directories, and file system APIs, and different uh, types of directory organizations, and how a file is accessed given a path for the file, and differences between hard link and soft link, and what is an inode for a file and what does inode contains. I hope you must be like you, if you have done the file system lab for lab 5, you must be very well aware of all these concepts. And uh, one important thing would be understanding the size of the maximum size of the file given the number of direct and indirect block addresses that are present in the inode. Right? So if we have, like, let's say 10 entries for uh, di- direct blocks, then you have 10 into size of each block as the maximum size of the file. And you can have an indirect block, and you can have doubly indirect block, triply indirect block, depending on that. The maximum size of the file varies. And also, given the configuration, the block addressing mode that is used in each inode, so the operating system has to perform in order to access a certain block number would be different. For instance, let's say a file, an inode where we use 10 direct addressing blocks and then 2 indirect addressing blocks. In that case, if I have to access block number 340, then I may need to do multiple accesses, right? First, I need to get the address of first indirect block, and then I again need to go into the first indirect block, and then finally find the block. Basically, this is similar to traversing page tables. You can imagine that each block addresses are like either there are direct page tables or second level page tables or third level page tables, so on and so forth. So, and you can imagine some questions where uh, you can throw in some numbers, right? Okay, each block access takes, let's say, X seconds. Now, how much time does it requires to access, let's say, block number Z, where the block number Z, depending on the number of blocks you need to access to get the absolute block number, the time will be different. Then we looked into journaling file system, where journaling is a redo log. Basically, we maintain all the operations that we are doing to the file system. And only after finishing each atomic transaction, that's when we commit the transaction to the disk. This allows us to recover from errors, especially when the error happened in between operations. You can always redo the transaction that is in the journal. That way, you can still maintain file system consistency without doing uh, file check, right? FSCK, doing the entire disk. That's the default way to do it. However, we can use journaling file system to avoid it. Okay, so any doubts on journaling file system? Then finally, we looked into distributed file systems, specifically NFS. We saw like file handles, how file handles are used in NFS, what are the different components of file handle, and why we need file handles. And NFS, we know it is stateless, and that provides all the operations on NFS to be idempotent operations. I mean, yeah. And clients They do an efficient, like they avoid seeing the network delays by maintaining client cache. However, client cache is not free. There are problems associated with client cache, specifically cache consistency issues. And we have seen a couple of examples, like a couple of methods in which consistency is maintained, and some problems in which like there is no perfect consistency, right? There could be some issues where a client might be reading old data, or even the data that is not present on the server. Uh, so that is the end. Those are the things that we will be covering in finance. And now we will do a quick review of things that we have looked into in lecture one, and making sure that we kind of covered everything, like tying the concepts that we thought we would learn to the things that we actually learned. Okay. So now we know for sure that operating system is a code that sits between programs and hardware, and it is a resource manager. It manages all the resources, especially files, pages, mutexes. At least three resources we have seen how operating system manages them, right? And at the end, we also saw it operating system as a giant interrupt handler. Like the DLXOS we have implemented is actually an interrupt handler. As you can see, once the process starts, the only way you interact with the operating system is through traps, right? That's it. There is no other way that you interact with the operating system. Any interaction goes through trap. And then we it's always a good decision to separate policy from mechanism. Mechanism it uh, is a way to do it, and policy decides when and what to do. Okay. So in case of, for instance, in lab 5, you can imagine the file system API, like the functions in files.c is the policy, and whereas the functions in dfs.c is the mechanism, because uh, the functions in dfs.c provides a mechanism to write to disk using DFS file system. Whereas you can imagine, uh, you can imagine a disk having different file system other than DFS, in which case you don't need to change the file system API. You just need to change uh, the underlying mechanism, which is instead of DFS, you can use, let's say, CFS or something. Right? And yeah, separation leads to flexibility, and it also allows, it also makes the debugging a lot more easier. Like if, like, try to, if you have done the implementation of Lab 5 without file system API, but by directly exposing DLX functions, then rather DFS functions, good luck. It would be a mess to debug certain issues. So, and we know there is no perfect OS, because most of the requirements are conflicting. Most of the requirements, they conflict with each other. So depending on the design goals of an operating system, few aspects of the operating system are given more preference than the other aspects. Okay, like Android, for instance, plays a major, like it places huge emphasis on security and efficiency, whereas Windows, for instance, or rather other operating system like real-time operating systems, for instance, they put more emphasis on efficiency and robustness. Okay. And the reason for this is because you don't know the future, right? You don't know how operating system will be used by the user. So there is no decision that is perfect, because you don't know how an operating system will be used. You just assume that the operating system will be used in certain way, and you make decision accordingly. So, and as you can imagine, most of the concepts, like one thing that you might have noticed in the entire course is most of the concepts are rather easy to understand, right? TLB, it's easy. Page tables, very easy. It's just a, as the name implies, it's just a table where you have virtual pages mapped to physical pages. That's it. Similarly, all other concepts are very easy to understand. They're not hard, they're just easy. But when you try to implement them, that is when you see the actual issues. For instance, uh, like lab 5, like you need to make sure that you hold, like you use locks when you are modifying inodes. In lab 4, you need to make sure that you are like, for instance, in copy on write, implementing copy on write, you need to make sure that you are decrementing physical, like the counter for physical frame after you resolve copy on write for the child, so on and so forth. There are these small details that you need to be careful while implementing, whereas they don't come up when you are trying to understand the concepts. So that's why I kind of realized that students, when they see the, when they hear the concepts and when they see the slides, they would assume that it's easy to implement, and that would lead, like, and they would start assignments very late. But when you try to implement, there are other small subtle bugs that takes a lot of time to implement. I mean, I'm pretty sure the initial implementation takes, let's say, 20% of the time. 80% of the time is to just fixing the bugs or just trying to get your implementation work. Okay. So, and most of the things, or like most of the implementation questions in our labs are just optimizations, if you think about it. Okay. So we I don't think we would we have any like novel or path breaking algorithms, but rather just small optimizations, very small optimizations, but overall they add up and they give huge optimizations. For instance, copy on write. Like at the surface, the optimization is so simple that you would not think that it would provide so much benefit. But try to disable copy on write on your operating system and try to use your operating system. Good luck. Opening a Chrome tab takes at least 40 seconds if you disable copy on write, by the way. So, so just a very small optimization, not at all fancy optimizations, very soft, small optimizations. The performance just shoots up as operating system becomes complex. These very micro optimizations are very effective. So, and we saw some concepts, but hopefully we did a lot of practice. Okay. So, uh, like, I hope you learned many things apart from operating system concepts. I hope you learned how to debug really bad code, especially uh, when there is no GDB. Yeah, I hope this helps you, not only in this course, but maybe in jobs or like in your future projects. So one thing to remember is this, the power of indirection. Just remember that any problem that you can think of in an operating system, in operating system, like in future, in your research or anywhere, try to think of an indirection. Okay. That will solve almost all the problems, especially when it comes to systems domain. Okay. Not only for operating systems, even uh, like anything related to systems, especially like security or even networking. For instance, like routing table, right? That's an indirection, by the way. BGP. That's like, if you know BGP, the entire BGP concept is just maintaining a bunch of tables, which is just again a level of indirection. So yeah, as system problems are like just indirection, just understanding where to put the indirection is a solution. Okay. Uh, yeah, we have seen various ways, various places where we used indirection. Actually, almost all the concepts that we have studied have at least one of the components, one indirection as one of their components. And we also saw we do certain optimizations based on some certain behavior of programs. Like we assume programs have certain behavior, and we design, or like we have optimizations assuming programs have such behavior, especially locality. We use locality left, right, and center in our operating systems, right? Like all the like TLB, paging, caching, everything is based on the principle of locality. That's why it's also important to write good programs, just because operating systems and even hardware few times assume that your program has locality and your hardware is optimized for locality. So if you write a program having good locality, it will automatically be faster compared to a program that doesn't have locality. Okay. So yeah, that's about it. Uh, yeah, that's the end of the course. Thank you for enrolling in this course. I know it's hard, especially uh, ha- like taking this course in a remote format. But I hope you have learned a thing or two from operating systems, and also from labs. I hope you have learned how to write good code and how to debug, especially operating systems code, when you see just a uh, random error. Like there are no nice, very good seg faults, right? You just see an illegal instruction error and good luck trying to debug that error. I hope that provided you. I mean, it must be. I'm pretty sure it's annoying at times, but honestly, that's a good experience, in my opinion. It makes you understand few uh, like minor details of engineering, minor details of systems engineering, especially. Uh, that's also why, like, if you look at systems research in general, like most of the papers, like to publish a paper, it usually takes like 1 to 2 years. Like, even though the idea is very simple, just getting the system up and running or getting the implementation rock solid takes really, really long time. Uh, that's like 90% of the effort. Uh, yeah, that's it. Any questions? Okay. So if you guys don't have any questions, good luck on the finals. And yeah, today is the deadline for Lab 5. Please make sure that you have submitted uh, your Lab 5 on time, unless you got an extension from me or from one of the TAs. Okay. Thank you. Bye. By the way, please fill up the course survey. Okay. Thank you.
Thank you.